All right, so we're in section 4.5, which is about the dimension of a vector space. So we were talking about the basis of a vector space, a basis for a vector space. Remember what a basis is? A basis is a set of vectors in a vector space that is linearly independent and that spans the vector space. So basically, a basis, you can build a vector space from a basis, and the basis is linearly independent. Right. So here's an important theorem. Not going to prove a lot of stuff. It's starting to get complicated, the proofs. We don't want to get too involved with the proofs in this course. If you want to take a second linear algebra course, maybe as an independent study, you could do a lot of proofs that are pretty intense. This one, we don't want to get too intense with the proofs, so we're just going to state the theorem. So if you have a vector space V, and it has a basis of n vectors, which we have V1 through Vn, then any other set containing more than n vectors, so let's say you had n plus 1 vectors or n plus 2 vectors or just more than n vectors, that set's going to be linearly dependent. Yeah, so remember your basis is linearly independent. So if you take extra vectors, sets with extra vectors are going to be linearly dependent. Okay, this directly leads to our second result. Second result's super important for establishing something later. It says if a vector space has a basis of n vectors, then every other basis of that vector space must also have n vectors. Yeah, so think about, for example, Rn, right? Rn is a vector space you're very familiar with. So we know epsilon 1, epsilon 2, and so on and so forth through epsilon n is a basis for Rn, right? You can build every vector in Rn from those n vectors, and they're linearly independent. But I mean, there are other bases out there as well. For example, you could take negative epsilon 1, negative epsilon 2, and so on and so forth. Negative epsilon n. That's a different set of vectors, but you can also build Rn from those, and they're linearly independent. But what's key is it's the same number of vectors. Same number of vectors. So every basis is going to be of the same size as basically we're saying. So since every basis is of the same size, we can define something called the dimension of a vector space. This is what we want to define. Definition. And I'll just say def for short. The dimension of a vector space V, and the way we denote that, we write it dim for dimension, is the number of vectors in any basis of V is the number of vectors in any basis of V. So for example, Rn has dimension n because it has what? N vectors in the basis. Epsilon 1, epsilon 2 through epsilon n. All right, here's another important theorem. I'm not going to prove this one. We don't want to get too involved in these heavy proofs. These are really heavy proofs in this section if you really want to prove things properly. Nail it down 100%. Here we go. Here's another result. If H is a subspace, of a vector space V, then the dimension of H has to be less than or equal to the dimension of V. Let's try to think about that. It's kind of intuitive. So out here we have a vector space, call it V. And inside of V we have a subspace. H, right? H is in here. So what we're saying is, if there's a basis for H, right? What is a basis? A basis is a set of linearly independent vectors which you can build H from. So what you can build H from, so you're going to have some vectors in here. Some vectors. Let me just put some points to represent vectors, some points. So the number of vectors in here that you can build H from is less than or equal to the number of vectors that you can build V from. So maybe out here you'll have like another vector that you can build. You can use, let's say, the vectors in H plus that vector out there in V to build all of V. So yeah, that's the idea. So however many vectors it takes to build H is going to be less than or equal to however many vectors it is to build B. That's because H is inside of V. So it's kind of intuitive. I'm not going to prove that. But we want to get just straight down to business. Just some background we had to have there. Just do some basic exercises. Let's see, so we talked about the dimension, right? The dimension. Dimension. For each vector space, subspace, let's see. For each subspace, how do you spell subspace? For each subspace, find a basis and state the dimension. Dimension. All right, number one. Here we have a subspace H. This one's going to be a subspace of R4. It's going to consist of vectors that take on the form B plus C, B, C, and 3B minus C. So B is our parameter, C is our parameter. These are just real numbers. This is a subspace of R4. Why R4? Because you got, what, 1, 2, 3, 4 entries going down. All right, so if I take a typical vector from here, what is it? B plus C, B, C, 3B minus C. Typical vector, right? We can see that we have a B in there. We can factor out a B, and that's going to leave us with a vector, and we can factor out a C. That's going to leave us with a vector. Let's figure out what are the entries. So for B, I got coefficients, what, 1, 1, 0, 3. So I'm going to put 1, 1, 0, 3. And for C, I'm going to have coefficients 1, 0, 1, negative 1. So I'm going to write 1, 0, 1, negative 1. So basically I can build all of H from these two vectors. These vectors are going to be linearly independent. So I'm going to write here basis for the subspace H consists of, let's just call it B for basis, the set containing these two vectors, 1, 1, 0, 3. It's my first vector, my second vector, 1, 0, 1, negative 1. Got a little extra business there on the side. All right, so what's the dimension? Well, the dimension, remember, is the number of vectors in any basis. So we have a basis right here that we found. This is dimension 2, right? 2 vectors. That's it. All right, let's do another example. Pretty quick, right? Pretty quick. Easy stuff. I've proven those theorems earlier, not easy stuff. It just took us probably an hour to prove those theorems. Don't want to spend all that time. All right, here's the second set of vectors, A, B, C, D, that satisfy the following linear system A minus 2B plus C minus D equals 0. That's your first equation. We're going to have a second equation in the system, A plus C plus D equals 0. And then finally a third equation, minus A plus B. I think that's plus 2D equals 0. So this is another subspace of R4, right? A subspace of R4 because there are 4 entries going down each vector. So all these vectors form a subspace. If you think about this, we're talking about a homogeneous equation. So it's solutions. So we're looking for general solution to this homogeneous linear system. We could call it the homogeneous matrix vector equation. I'll just write homogeneous linear system, right? We got zeros on the right side. So essentially what you can do, you can create an augmented matrix and put what, 1, 1, negative 1 down the first column, negative 2, 0, 1 down the second column, 1, 1, 0 down the third column, negative 1, 1, 2 down the fourth column, and then augment that with the 0 vector. And row reduce this using your RREF function. What happened there? I wasn't supposed to do that. It was in writing mode. All right, so what we're going to have when we row reduce, we're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1, negative 1, 1, 2, and on the right, 0, 0, 0, obviously. It looks like we have what? How many pivots? 3 pivots, so A, B, and C are basic variables. And it looks like D is a free variable. Right, this column doesn't have a pivot, so D is free. So what we have to do, we have to find A, B, and C. So let's find C first. You work in reverse order. This is back substitution, right? We're going to use this here. We're going to have what? C plus 2D equals 0. That's what C equals minus 2D. All right, let's find B. Let's use the second row for that. Got that pivot there. We're going to have B plus D equals 0. That's B is negative D. All right, let's find A. In terms of D, let's use that first row. We're going to have the equation A minus D equals 0. We can solve A equals D. So when we write our general solution, D is going to be free, right? General solution. All right, so what do we got? A equals D, hold up. B equals minus D, C equals minus 2D, and D itself is free, so D just stays as itself. Now when I put this in parametric vector form, my general solution, parametric. Vector form of the general solution. Call it X. So in the first place, I would put a D. In the second place, a minus D. Third place, a minus 2D. In the fourth place, just stays a D. That's free, and we're going to factor out a D. And when we're factoring out a D, we're going to put coefficients here. See, 1, negative 1, negative 2, 1. So you can build, so this is actually what, a null space, right? It's the solutions to this homogeneous linear system. Remember, solutions to a homogeneous linear system form a null space. So this is a null space, actually. It can be built from a single vector. So the basis here, what color am I going to use? Purple. Basis for H is going to be, let's call it B for basis. It's the set of all vectors. Well, just a single vector. 1, negative 1, negative 2, 1. You can just build the entire null space from that single vector, right? Just scalar multiples of that will build it all. So that means the dimension of H in this case is 1, right? One vector can do it all. So pretty easy, I think. I think we'll stop there and maybe pick up in another video.